Good morning, Michael.
Good morning, Matt. Hope you're doing well.
Really well. What do you mean by the wonder of areas?
Well, I'm going back to some of our earlier videos when we were talking about defining functions, and we used areas to define the functions and all sorts of interesting properties. So like the sine function, cosine function, there were the hyperbolic functions. We even did exponential using areas instead of some sort of limit.
You know, I remember when we did areas, a lot of the traditional identities in all the trigs that you just mentioned were just obtained by adding up areas.
Exactly. So for instance, in the trig functions, we had little pizza slices, a wedge of pizza, and we added up the areas of the pizza slices. That gave us all the trig identities that we wanted.
So will we get something like that with this wonder of areas today?
We're going to go back to areas again today. We're going to look at the exponential function, and from it, we're going to come up with the logarithm function.
Oh, let's see how it goes.
We should mention the logarithm function goes way, way back to a guy named, was it Napier?
Napier in the 17th century.
17th century, that's a long time ago. And so even before calculus, people were talking about logarithms.
Yeah, and it's amazing what he did. And the algorithm is non-trivial.
So we'll start this way. We had a rectangular
1 over x.
1 over x, rectangular hyperbola. Y is equal to 1 over x. And the way we define exponential function was, again, using an area. We started off at the point x equal to 1. Do a straight line up. And then I take a little chunk of area underneath here. So there's some area there. It's not quite a rectangle. It's not quite a trapezoid, but you can imagine there's an area there. And then we define this point here as the exponential of a.
So x is equal to x of a.
Exactly. X here is the exponential of a.
So isn't that wonderful? Because now we could have this just purely geometrically. If we have a computer and we plot these really finely, we plot these, we can get out a ruler or calipers, measure areas, and get this relationship without doing any series, any integrals, any limits, just geometry. Wonderful.
That's exactly right. So there's no limits, no fancy integrals, nothing like that. It's just area and this definition here. Now I want to define another function called the logarithm. Okay.
Yeah, well, we know what that is if we have a power law. So we could start with that, like y equals x to some power, right?
We could do something like that, but let's avoid all the algebra and just look at our picture here. This equation defined exponential. I'm going to go the other way around and just say, I'll take the logarithm of x and say that is equal to a, the area.
Now, when you define log, there's usually a base, 10, e, 2, whatever. So
right.
When you're saying this, exactly what are you saying here?
Well, this one I'm calling, people call this the natural logarithm, and you'll sometimes see it written as ln of x, which is fine. Other people will write it as logarithm to the base e, where e was that special number where the area you get is exactly 1.
I think that's how you define these points.
That's how you define those points. And you're right, there are other types of logarithms. For instance, engineers like to use log base 10. Okay, they're all very closely related. Okay, so I'm just going to make my life simple, and we'll just talk about this log, and we'll worry about the other ones
and
as
I
well.
guess the context is provided by your figure here. So we know it's not base 10 and all that stuff.
Right.
We just work with this area with this definition.
That's right. So let's do a couple simple things. If I was going to have an area of A equal to 0, what's the corresponding value for x?
Well, it's got to be 1.
So x is equal to 1. So looking at my formula here, that tells me that the logarithm, x is 1, so logarithm of 1 is equal to 0. So that's an interesting fact about the logarithm function, right?
Yeah.
What else can I say? Remember there's a special place, E, where if I went far enough out here to get an area of 1, this gave me a value x is equal to e, which is roughly 2.71.
828.
Okay, I'm not going to fill up my screen, but you're right. It's got many, many decimal places. It goes on forever. But this is a special number where if I go along this curve until about 2.71, I get an area of equal to 1. Now, if I look at my log function, what does that tell me?
It says log of e is equal to 1.
E is equal to 1. That's what we mean when we say the base of this logarithm is e. If we had base 10 logs, we'd find out the log of 10 was equal to 1.
Log
But
10,
we just have log of
10
e equal to
10
1.
and so on, yeah.
Okay.
This is a wonderful result. Can you summarize exactly what that means? And is it also related to something we've studied before in a slightly different context?
Yes. So what's happening, I'll say the word. One of the functions is the inverse of the other. The sort of like the way the square root is the inverse of the square. So what happens here is you take an area of 0. If you exponentiate it, you get the number 1. And then you take the logarithm of that 1 and brings you back to 0. Same thing here. You start off with 1. If you take the exponential of 1, you get the number e, which is about 2.71. And then you apply the logarithm to that, you get back to 1. So 0, 1, 0, 1, e, 1.
So we've established this basic geometrical setting and the forward and backward functions. Where do we go from here?
Well, let's write down this forward and backward thing. So basically we're saying if you take an exponential and then take a logarithm, you get back the original area. So this was this formula. Logarithm of the exponential of the area is equal to the area again.
Oh, and that
Okay.
really does show that these are inverses.
It does show that the inverses, and it goes the other way as well. So if I take the exponential of a logarithm, and now I'm going to use x because that's how we were using our formulas there, this brings back to x. So this is also true. If you take the logarithm of 1, you get 0. Take the exponential of 0, you get 1. So it brings you back to 1.
Yeah, which is the first result.
The first result.
Okay, now that we've got all these connections, let's see where it carries us forward.
Okay, so remember, with sines and cosines, we had these magic formulas. It's cosine of x plus b, or something like that, or sine of 3 plus 5. And there's some magic formula. There was a nice formula for exponential, and I'll remind you what it was. It said, okay, so exponentials, we work from areas. If you take the exponential of the sum of two areas, this gives you the product of the two exponentials. This was something we argued with a bit of geometry, a little bit of linear algebra, perhaps. But this is the exponential relationship. So if you take the exponential of the sum of two things, you get the product of the two things.
It reminds me when we did it for sine and cosine and the hyperbolic sine and cosine, the results were more complicated. And here it's a lot simpler.
That's one really nice thing about this exponential. In fact, it's very closely related to something like if you say 2 to the 10 is equal to the same thing as 2 cubed times 2 to the 7th. So
Okay.
3 plus 7 is 10. That's kind of where this is coming from.
That's good. So
Okay.
let's go and see how we can relate it to our definitions and your summaries.
So let's take the logarithm of this equation. So these two guys are equal. So if you take the log on both sides, so this will equal the log of the other side. XA times XB. Now, one of these is very easy to solve. Because log of exponential, what is log of exponential?
It's the argument a plus b,
So, right, you get an a plus b here.
because they're inverses
That's right.
right here.
Now, this side, I can simplify a little bit. If I think of this exponential of a, it comes from some sort of x, right?
Yeah, so maybe you want to call it a and b, some kind of x associated with an
Maybe
x.
x subscript a. Could
Yeah,
I do that?
that's good.
So I'll call this guy, well, can I write it this way? The first guy I'll call x subscript a, and the second guy I'll call x subscript b, right?
That's fine.
Okay,
So now we have to use the result here.
right. So this a came from an x, but
Sub
that
a.
x had a special name, right? So we'll call that log of x sub a. And then I add to it a logarithm. What is b?
Well, it's right here. It's log of
so I have
xb.
so it's the xb. So the sum of these two logs is the log of the product. So it's kind of the reverse of what the exponential did. The exponential took a sum and turned it into a product. The log takes a product and turns it into a sum.
Fantastic. What a wonderful result. And all based on geometry.
Excellent. Thanks, Matt.
Thank you. Wonderful.